allow me for some reason. I think it's this one, right? Yeah.
Okay, so our next speaker is Santiago Oviedo-Casado, who is going to tell us something about low-frequency signal detection by correlated Ramsey measurements.
Yeah, so that's basically the talk. I mean, like Shlomi said, my task now is to convince you that this thing that we propose works for low frequencies, and of course that low frequencies can be important, I guess. But first of all, thank you for remaining for the short talks, and thank you for the organizers and the funding agencies and everybody for this amazingly nice place and hotel and venue and everything. And also to the other speakers for the nice talks. So yeah, I work for Alex Redker, who just came in. Thanks. And actually, this work, I didn't do it with him or with a group. I did it with some collaborators, old collaborators in Spain, and we just almost finished. And yeah, basically, it's what the title says. I will try to convince you that low frequencies are important. Typically, you cannot detect them with quantum probes, and I'll go to what low frequency signals means, what are low frequencies, and to tell you what we propose to detect them. This is all theory. I'm just trying to convince someone to do the experiment. Yeah, it's a bit of the motivation. I mean, it's important. Low frequencies are everywhere, and they are quite important in many fields, some of them there, and apparently even for alien life detection, something to do with the 21 centimeter hydrogen line or something like that. They can encode information there. But many other places, and they are usually inaccessible with quantum probes, and I'll show you in a little while. But first of all, what do we mean by quantum detection or detection of signals with quantum probes? Well, you put a superposition state on your probe, let it evolve, and it interacts with a signal that I put there, and this signal causes a phase to accumulate on your state. You measure, the measurement tells you information about the parameters of the signal. They are encoded there. You estimate them. That's it. The problem is that if you are sensitive to the signal, you are sensitive to noise, of course. And just to set it here, I define the T2 star noise, the dephasing noise. And no, it's not the standard for the superconducting community, maybe. And then T1 noise or relaxation noise. Those are the basics. And so when you have noise, you run into problems. And to solve these problems, or to mitigate them at least, we apply control sequences. The Ramsey that you just heard about is the very basics. You almost do nothing. You let it evolve and then measure. And this means the probe is more sensitive to the lowest frequency component of the whatever you have around, typically frequency 0. And if you want to detect some different frequencies, Alex said an intuition about what dynamical decoupling is. I have another one. For me, it's like you have to make your quantum probe rotate, and to rotate at the same angular frequency as the frequency of the signal that you want to detect. In that way, in the frame of reference of your qubit probe, it sees the signal as static, then it's more sensitive to that signal. That's it. It's like doing Ramsey, but in a different frame of reference. Or you can see it as creating a frequency filter, blah, blah, several other interpretations. The problem is, yeah, you have to make your probe rotate. And you have to make it rotate at the angular frequency of your signal, right? So typically you apply pi pulses, so the techniques and the spatial separation, the time separation of the pulses has to be similar to the frequency that you want to detect. And this means that your sequence, your dynamical decoupling sequence, has a fixed duration. You cannot change it. You can play around with it, but you cannot change it. And although, because you suppress sensitivity to other frequencies and so on, nice properties of dynamical decoupling, you enlarge the dephasing time to a decoherence time, some function of the number of pulses, other things. Sublinear, this alpha is typically smaller than 1. I mean, otherwise it would be magic, not physics. But it means that if your frequency is smaller, or the inverse of the frequency is larger than the T2 of the probe that you get, you can never match it with a dynamical decoupling sequence. You can never match these rotations, and therefore it won't be sensitive to your signal. And that's the problem. That's what I mean by low frequencies on the title, frequencies that require a measurement time or a dynamical decoupling sequence duration that is longer than the T2 that you can get. So it's useless, yeah, for low frequencies. And even if you could do something, well, you are limited by the T1 anyways, so yeah, that's the problem. So what do we do about it? And here the key is that the signal I showed, it not only has frequency, it has also phase, right? And this phase, I mean, typically you define the filter function, which is the corresponding of the spectrum as the absolute value of the phase that is accumulated on your superposition state. But that's a definition, it's the absolute value squared, but you can also define as the real value squared. Why not? Or the imaginary part. I mean, you can play with that. And if you do that, this means that, I missed a parenthesis, it means that you are sensitive to the phase, you are including sensitivity to the phase. If you include sensitivity to the phase, as you can see, your filter function kind of bends. Typically, this would be straight bars, but it kind of bends. And this means, for dynamical decoupling, doesn't matter really much, but for Ramsey, it means that the maximum, now it won't lie exactly at the zero frequency, but slightly different from zero frequency, which is the nice thing. It's a very low frequency, but not zero. So could use that. And nice thing is that there are already protocols using for measurement with quantum probes, in particular the Q-line family or sequential measurements, which allow you to be sensitive not only to the frequency, but to gather information in your signal about the phase of the signal. It requires carefully measuring the time and separating your measurements by a specific, very specific time, and then some post-processing and so on, but you can do it. And the Ramsey sequence, the nice thing about it is that as long as the duration of the free time evolution of one of the Ramsey measurements is smaller than the T2 star, so the dephasing time, this has no frequency matching requirement, no anything. And so that's what we propose, use correlated Ramsey measurements in the fashion of what sequential measurements or Q-line proposes to detect low frequencies. So now I'll try to convince you that this can work, and so that's what we propose. Instead of doing this complicated dynamical decoupling with several passes, blah, blah, won't work, do the same, with the same duration, right? The same amount of Ramsey measurements equivalent to the duration of your dynamical decoupling sequence. That's our benchmark. We want to compare these two things, same duration, and show that we can detect low frequencies versus the dynamical decoupling that you cannot use it. And to do that, it was already introduced, the Fisher information, nice. Basically, it's just a measure of how much error will you have when you try to estimate the parameter that you want to estimate from your signal. So the more information that you gather, the higher the Fisher information, the smaller your error. So we will be comparing, or we compare for the same duration, the information that you gather on a correlated Ramsey of n Ramsey measurements and dynamical decoupling. And that's how you calculate it. So you need the accumulated phase, and the accumulated phase is very simple to calculate, just this integral over the signal for Ramsey, and you can already see why it is sensitive, the sensitivity to the phase, what gives you these nice properties. I mean, the sinc function is what dominates the filter function or the spectrum. Sinc peaks at 0, that's why it's more sensitive to the zero frequency, but the cosine, it modifies this slightly. You can show it mathematically. It's a transcendental equation, so it doesn't have the maximum at 0, but at the solutions of this equation. And for the dynamical decoupling, you can also calculate it. It's a slightly more complicated integral, nothing to say about it. And you can show that what I told you before, this intuition that it's put in the qubit probe to rotate at the same angular frequency, it's a nice way to view it. If you do this approximation for if you take the limit in which the frequency of your dynamical decoupling is very similar to the frequency of your signal, you can see that you recover the Ramsey phase accumulation with some constant in front, but shows you that that's what you are doing with dynamical decoupling, going to Ramsey in a different frame of reference. But well, now we have the accumulated phases. There's our money. We can calculate with them the Fisher informations. It's just an additive quantity, so for correlated Ramsey, you just sum them up. And so we tried it numerically, just compare the two sequences. And so you can see for a low frequency, which requires a duration of your sequence, which is longer than the T2 time. And here, this is important. We are considering that the T2 grows linearly with the number of pulses, just to be on the extreme case of favoring as much as we can dynamical decoupling. And so we find that, so the line marks the logarithm of 1, 0 in this case, because it's logarithmic scale. It shows you that you can always find a duration of the Ramsey sequence with which you can measure or you can have much more information about the frequency of your signal, which will allow you to estimate it with much less error in the end, right? Than if you try to do a dynamical decoupling sequence that in principle it should fail. And we also saw that, I mean, this overhead time means when you do correlated Ramseys or Q-dyne in general, after it, well, with any sequence, but after the measurement, you have to reinitialize the qubit and so on. So this is kind of wasted time in a sense. You are not measuring. So to be fair, we compare our one dynamical decoupling sequence of duration t with several equivalent correlated Ramsey measurements, including or considering this possible overhead time. So yeah, of course, the more you reduce it, the better. But it also shows that in this space, so if you have frequencies that, or host period is longer than the T2, yeah, dynamical decoupling sequence, no good, use correlated Ramsey. But what happens if you have frequencies that are between the dephasing time and the decoherence time, so the T2 star and the T2? Well, still, if you can manage things with the overhead time, you better still use the correlated Ramsey, so do correlated Ramsey measurements. And because this was numerical with accumulated phases, long formulas, difficult to interpret what's going on or to see it or to use it to design sequences to calculate the parameters. You can take the formulas for the Fisher information, do some easy approximations in the low frequency regime, get simpler formulas to work with, and calculate what we saw the gain before, and you can see that it gives you the exponential increase on the so it's an exponential increase on the gain, so an exponential gain on the Fisher information if you do correlated Ramsey with respect to dynamical decoupling whenever you are in the low frequency regime that I defined. And this is nice. This gain that we defined shows that you have more information if you do correlated Ramsey than if you do dynamical decoupling in this regime of low frequencies. But so far, it doesn't tell you if this information is sufficient. I mean, it might be that the gain is greater than 1, but the information is still not enough to estimate the frequency that you want to estimate. So we also separated it, calculated or plotted the Fisher information separately. So in red, you can see, well, we define Rayleigh criterion for estimation of the frequency, below which the shadowed region means you won't gain sufficient information. Your mean square error would be too big to consider that you've estimated anything. And so you can see the dynamical decoupling, even if the growth of the decoherence time is linear with the pulses, goes to the shadowed region very fast. But with enough measurement time, and regardless of the phase, because typically what you would do is measuring measurement vectors with different phases, and then average, you can go to very, very low frequencies if you need to go to lower frequencies, just increase the measurement time, and you can always be above this shadowed region. And also, we calculated the sensitivity, which is just defined also through the feature information, and you can see that if it grows, the T2 grows linearly, like ideally it could work, maybe you could some point reach something, estimate something, but yeah, again, our proposals should work much better. So, as I said, we just finished this work. Because I'm in the conference, I didn't have time to sit down and do the submission. Now, I'm not sure if I should patent it before doing the submission. But yeah, if you're interested, I'll probably put it in the archive soon enough. And yeah, I hope you convinced you that if you want to measure low frequencies, this could be a nice way to try and to go about it. And with that, well, I would like to thank in the corner the two collaborators from Spain with which I did this work, and in the center, the amazing group from Alex. And yeah, thank you.